Hi, this is Mrs. Marita. Welcome to section 4.1, Solving Systems of Equations by Graphing. Please turn to page 76 of your student companion. We're going to complete a couple examples today on solving systems of equations by graphing. But let's take a few notes first. So you might be asking, what is a system of equations? So a system of equations is a set of equations, so two or more equations, where we want to solve for the variables that make both or all of the equations true. We're just going to be looking at two equations, but later in algebra, you could have more than two, 3, 4, lots more. But for us, we're just going to stick with two. And recall two of our linear forms, slope-intercept form, y equals mx plus b, and standard form ax plus by equals c. We use the standard form to graph with the intercepts. Point-slope form was a good one too, but today we're just reviewing with our slope-intercept and our standard form. In Chapter 4, we're going to look at multiple ways to solve systems of equations. That is, we're going to look at multiple strategies to come up with those x-y pairs that solve both equations. For 4.1, the section we're in today, we're going to look at a method of solving by graphing. So for example 1, we're going to graph both of these linear equations, and then we'll see where they intersect. Their intersection will be our solution. For our first equation, our slope, m, that's the positive 1/2, and then our y-intercept, b, is -2. So we're going to start at our intercept, -2, and then we'll use our slope to go up 1 and over 2. And then we'll connect. And then for our second line, our slope will be 3, and the y-intercept will be -7. So we're going down -7, and then our slope 3, again, we could write that as 3 over 1. So I'm going to go up 3 over 1. And for solving by systems, I'm going to keep going and hope that I hit my other line. So I'll go again, up 3 over 1, perfect. And that point of intersection, we're going to look right here. So that point is over 2 and down 1. This is going to be our solution to our system. And so for our answer, we'll say x is equal to 2 and y is equal to -1. Or you could write it in the parentheses as your solution set. Let's try part B. Again, go ahead and draw your axes. This one has to go all the way down to the bottom to fit this top line. And so our first line will have a slope equal to 2 or 2 over 1, and our intercept will be +10. So that's going to be way up here. This is my +10 if you count up. To use my slope, I could go up 2 over 1. That works, but that's kind of weird going off the graph. So we'll go the other way. Instead of going up and to the right, we can go down 2 and to the left. Down 2, to the left 1. And so this will be my first line. I do my best. And then my second line will have our slope is -1 over 4, and the intercept is 1. So I start at +1, and then my slope, I'll go down 1 and to the right 4. Now I want to see where this hits my graph, so I'm going to go the other way as well. Up 1 and to the left 4. Perfect. And so we can see that this point of intersection is at -4, +2. So my solution set is -4, 2, or we can say x will be equal to -4 and y will be equal to 2. Before we move on to example 2, let's look at some different types of solutions that we could see with two lines. The first type we could see is a one solution set. So one solution, this is where you could graph your two lines and they'll intersect in a single point. The second type you could see is a no solution set. This is when we have parallel lines. The last solution type is kind of weird to draw. So this example, we could have a line, so we graph our first line, but then suppose you graph the second line and it's exactly, oops, I kind of missed. Use your imagination. It's exactly on top. This example, we would say there are infinite solutions. This is when both of your lines are exactly the same. So let's try this. We want to graph the systems of equations with infinitely many or no solutions. Part A. So for part A, our first line will have a slope of 1/2 and an intercept at 7. So we start with our intercept, plot your intercept at 7, and then we're going to go up 1 over 2. Oh, we ran out of room. How about we go down 1 over 2? There we go. So this will be our first line. And now we'll plot the second. Now the second line is in our standard form. So we're going to look at our intercepts. What do we get when we plug in 0 for our x? And what do we get when we plug in 0 for our y? So if we plug in 0 for our x, then this whole term cancels out. Negative 8y is equal to 12. Divide both sides by negative 8. And we end up with our y is negative, 12 over 8. I can reduce both of those by 4. And so we get 3 over 2, or negative 1 and 1/2. That would be my y, negative 1 and 1/2. And now to find the second intercept, this will be my x-intercept, we're going to plug in 0 for the y. And so we end up with 4x is equal to 12. Divide both sides by 4, and we get our x is equal to 3. So when x is 3 and y is 0, that'll be our second intercept. Some of you guys really like rearranging these and putting them in slope-intercept form. You could do that too. So let's graph our two intercepts. Our first is at 0, negative 1 1/2. That's kind of weird right there. And then our second is over 3 and up 0. So when we graph these, we should see that the slopes are the same. That's kind of tough to tell because we have this fraction we're graphing, but if we went up 1, so if we went up 1 over 2, yep, we'd end up on the same line. And so because these two are parallel, we say there is no solution. So our final answer, that's all we write, no solution. Now let's try part B. Neither of these are in a very nice form, and like we saw before, we're going to get some fractions if we use our standard form and our intercepts. So I'm going to go ahead and try to put this in slope-intercept form. So I'm going to look at this first equation. 3x plus 2y is equal to 9. And so I'll subtract my 3x from both sides. Again, I'm trying to put this in my mx plus b form. And I get 2y is equal to negative 3x plus 9. Divide everyone by 2. And this first equation works out to be y equals negative 3 over 2x plus 9 over 2. That sure looks like fun to graph. And then the second equation, I've got 2 over 3y is equal to 3 minus x. I want to get rid of this fraction action, so I'm going to multiply everybody by 3 over 2. 3 over 2. There we go. And so on the left side, my 3's and 2's will cancel. Hooray! I just get y. That's not so bad. And then when I multiply, if I distribute this in, I end up with, 3 over 1 times 3 over 2. 3 times 3, multiply my numerators, I get 9. 1 times 2, my denominators, I just get 2. And then minus, 3 halves times negative x, that's not bad. That's just negative 3 halves x. That's kind of weird in that order though, so I'm going to rearrange. And I get y is equal to negative 3 halves x plus 9 over 2. Let's look. If we take a step back and look at our two equations, we have negative 3 over 2x plus 9 over 2, and our second line becomes negative 3 over 2x plus 9 over 2. They tried to make these look really weird so we wouldn't recognize they're actually the same line. So we're not even going to graph these, we're just going to say these are the same line. Hooray! We don't even have to graph. And so this is an example where if you did, you'd have the exact same line. And so we say this one has infinite solutions. That's it for 4.1, just lots of graphing lines and seeing if they intersect. Make sure you copy down all your notes and bring your questions to class.